Thank you for attending this workshop. My name is Zaida Piedra, and I am a technical application scientist at BioLegend. And in today's workshop, I would like to show you some of the optimized panels that we have developed at BioLegend, but also I would like to walk you through the process that we use to build these panels. And with that, I would like to start highlighting some differences between the spectral and the conventional cytometry. I hope you can see well my pointer. That is going to be very useful for later slides. Spectral cytometry is a new technology that allows the analysis of single cells using a fluidic system similar to the conventional cytometry, and it's an excellent tool for multiparametric analysis. However, even conventional and spectral cytometry share some similarities. They have some differences that they lie mainly on the detector system. On one side, the conventional cytometry uses dichroic mirrors that split the light using bandpass filters. But on the other hand, the spectral cytometry uses prisms that are going to disperse the light, and this light is going to be later collected using an array of detectors. Because of these differences, the conventional cytometry collects one peak of emission at a specific wavelength, while the spectral flow cytometry collects the entire spectrum of emission across all the wavelengths. And because of this difference, now the spectral cytometry allows us to use new combinations that we cannot use in the conventional cytometry. As I'm showing you here, this example, that is PE and spark yellow-green 581. These two dyes, they are very similar and they have a high level of overlap on conventional cytometry. However, the spectral cytometry allows us to identify small differences between these two dyes, as it is the case of PE, for example, that has this peak that is absent in the spark yellow-green 581. And these small differences are enough for spectral cytometry to unmix these two dyes and have a good resolution for both. The spectral cytometry is a technology has been quickly advancing, and now we have more cytometers that come with multiple channels that allow us to expand our panel's capability. Together with the cytometers, they also come with a technology that has a more advanced algorithms to do unmixing, compensation, and even give us the option to subtract autofluorescence. And together with the cytometry technology, now companies as BioLegend, we are developing spectrally unique dyes that you can use during the large panels of spectral cytometry. And we, of course, now we have the options of customize those conjugates and antibodies. All this together combined is giving us the opportunity of expand our panel's capabilities, and now we can analyze more than 20 colors in a same panel. At BioLegend, we are proud ourselves of offering more than 30,000 products that you can use to successfully characterize your research. However, as scientists ourselves, we empathize that having so many markers, so many clones, so many dyes, and so many conjugates can be a bit overwhelming and could be hard to decide what to include in your panels. And also, if you add some unknown conditions as the buffers, your protocol, plus what will be your gating analysis, what is the best gating strategy, all these together can lead you to have many errors during the optimization, and you can spend a lot of time trying to get a very optimized panel with more than 20 colors. However, given the good amount of data that you can get using a spectral cytometry, this is a very well worked with process. And what about if at BioLegend we can help you to do that process even easier? Well, at BioLegend, we have unique knowledge about clones, fluorophores, and protocols that can help you to build your panels. And you can use our tools in our website where we have a panel builder, or work with our technical support team. And together with you, we can help you to build the panels, but both tasks will require a constant interaction between you as the user and BioLegend. But now, to do your research even easier, we are offering the pre-optimized panels. These panels, you can quickly acquire them in our website, and you can just start using them on your research. All these panels have been developed by scientists that have an extensive experience using the BioLegend products, and they have also a lot of experience building very large panels. All the panels have been optimized for the better usage of the markers, the clones, the fluorophores, the conjugates, and they come with optimized protocols and gating strategies. All these together can help you to have a deep visualization of myeloid and lymphoid lineages. And I invited all of you to visit our website where you can find more information about the optimized panels that we have available. Now, to give you some insight on how we build these panels, in the following slides, I would like to walk you through the process that we follow to build our human general phenotyping panel that is a 27 color panel that we have optimized. And if you are familiar building panels, you are gonna see that we follow some of the standard rules. However, we put our unique knowledge on building those panels that are gonna help us to successful optimization. And from the general rules, we first select the antigen of interest, where it's important to know where is that marker expressed and if it is co-expressed for more than one cell type, and what is the level of expression of the molecules that we want to analyze. Then it's important to select the fluorophores. And here we need to, if possible, we need to use unique dyes with unique signatures, but also we need to know what is the brightness level of our dyes. And finally, we are gonna assign those markers with those dyes. And here we have to keep in mind what will be our hypothetical gating strategy to minimize the spreading error. And also we have to consider some reagent availability and some limitations that we may have as it is the cytometry configuration. So let's start building the panel. And first we are gonna select the antigen of interest. As I mentioned before, this is a human general phenotyping panel. And in this panel, we would like to identify from the myeloid compartment monocytes, basophils, and dendritic cells. And from the lymphoid compartment, we are going to identify B cells, NK cells, and T cells. Once that we have identified the populations that we want to characterize, we are going to list out the markers that we are going to use for those cell types. For example, for monocytes, we have selected CD14 and CD16. For basophils, we are going to use the combination of CD45 and CD123 to identify those cells. For dendritic cells, HLA-DR, CD11C, and to go even deeper and analyze some subpopulations, we are going to include CD11C and CD141. For NK cells, CD15 and CD56. For B cells, we are going to use the classical CD19 and CD20, but to identify naive and memory B cells, we are going to include CD27, IgD, IgM, and CD38 in this panel. And finally, for the T cells, we are going to include CD3, TCR gamma delta, CD4, CD8, and to look on the Tregs, we are going to include CD25 and CD127. For a further analysis in effector and naive cells, we are going to include CD45 array, CCR7, CD27, and CD28. Once that we have selected the markers, let's move to the next step, that is selecting the fluorophores. When selecting the fluorophores, it's important to know what is the similarity index between these fluorophores that we want to include in our panel. And I'm showing you here an example of a matrix that is comparing all these dyes against each other to tell us how similar they are. And for example, with values that are close to 0, that means that the signature of these dyes is very different. But when the values are close to 1, that means that they have some similarity. In addition of knowing this information, we have to consider also the reagent availability. And if possible, we would like to select more dyes than what we initially need to have some flexibility. And now let's take a look at each dye, each laser, or the dyes on each laser. And on the violet laser, you can see that there are many dyes that have a low similarity index. And for this reason, at BioLegend, we tend to pack this laser with multiple brilliant violets. And we have an extensive experience using all of them together in our multicolor panel channel. and they work really well. However, we have other combinations, as it is Pacific Blue and Brilliant Violet 421. Those two have a high similarity index of 0.81. That means that they are similar. However, because both dyes have high reagent availability, we want to include them in our panels. And the technology of spectral cytometry allows us to use them. We just need to take care and take in consideration some aspects. For example, we want to assign these two markers to opposite cell types. That way we are going to avoid to plot them against each other. And when assigning the rest of the brilliant violets, we are going to have the same criteria, trying to minimize the spreading. Now, in looking into the blue laser, here we have multiple dyes. All of them have a high similarity index higher than 0.97. That means that we cannot have a good resolution between them. They are too similar, and we must choose only one of those. But we have other options as the spark blues that you can see here. They have a relatively low similarity index, and they are a great option when we are building or when we are doing a panel expansion. And also we have our PCP fire tandems. They have low similarity index, and they work very well with large panels as they peak in areas with very few existing dye options. And now in looking at the yellow-green laser dyes, here at BioLegend, we have experience using PE together with the spark blues in our multicolor panels. So we know that they can be resolved very well. And as I mentioned in the introduction, spectral cytometry allows to identify a small difference between these two dyes. And for that reason, we can include them in our panel. And when we start working with very large panels, we are going to have the necessity to include dyes that are very similar, as it is the case of PE5 and PE640. Those two have a very high similarity index, 0.93, but because their maximum peaks are in different channels, we can still put them together in our spectral cytometry panels. But if possible, we would like to reserve those combinations for very large panels just when it's necessary. And lastly, looking on the red laser, we are going to have the combination of APC, Alexa Fluor, and Spark NIR 685. They have a high similarity index, but we still are able to resolve them. We just need to be careful on how we assign the markers to these dyes. We want to have them in opposite cell type, and here it's important to have an idea of what will be our gating strategy when we assign these dyes. Then, similar to the previous example, we have another combination that is Alexa Fluor 700 and Spark Red 718. They have a high similarity index, but their maximum peak are in two different channels on the red laser. So if necessary, we could include them in the panel. And finally, APC size 7 with APC Fire 750. They are too similar. We are not able to distinguish them, so we must choose only one of those. And jumping a little bit forward, I'm listing here all the dyes that we are going to use for this panel. And I'm going to just highlight or point out some combinations that we didn't discuss previously when looking into each laser, as it is the case of the PCP Psi 5.5 and PE 700 that you can observe here. Their similarity index is 0.76, is relatively high, but here just a careful gating strategy should be sufficient to maintain the resolution of both dyes. And for those markers where the similarity index is higher than 0.8, we have to be very careful on how we assign the dyes for those, or the markers for those dyes. And once that we have selected the markers, now let's move to the next step, that is assigning the fluorophores to those markers. Here we normally start with low reagent availability, so we want to assign those first. But in this particular example, the human general phenotyping doesn't have that problem because all the markers that we have selected, they have high reagent availability. So I'm going to move to the next step, that is fill the markers with low expression on those dyes that have bright levels of, or are brighter, sorry. And here, if you are not very familiar building the panels, listing out the dyes from the brightest to the dimmest, and the markers from the lowest to the highest expression is very useful to help you to do that matching between the dyes and the markers. And finally, we are gonna select our viability dye. So in working with the large panels, we know that our zombie NIR is an excellent option to include in large panels, as it doesn't block popular channels or mix very well with the red lasers and leaves all UV channels open. And for that reason, this will be our option in this panel for today. So I'm listing here all the dyes that we have selected for this panel, from the brightest to the dimmer. And in the opposite direction, we are going to have the highly expressed molecules that we selected at the beginning of this panel, and then the ones that are low expressed or that they have low frequency. Now, when working on this panel, the first step will be to identify those markers that are the brightest, and what is the markers that are very similar to those or that have a point higher than 0.8 similarity index, because we want to start assigning the markers for those as our first step. And I have summarized here, for example, from the violet laser, we are going to have the combination of brilliant violet 421 with Pacific blue. In the yellow-green laser, we are going to have P and spark yellow-green 581. And in the red laser, we have the combination of APC, Alexa Fluor 647, and spark NIR 685. And let's start with the brilliant violet 421. For the brilliant violet, this one is a very bright dye, and it has high reagent availability. For this panel, we have multiple markers included for T cells. And in this panel, we want to characterize central and effector memory T cells using CCR7. That means that we need a marker that is going to give us a good resolution to identify positive and negative cells. And we know from internal experience, the CCR7 conjugated with the brilliant violet 421, and specifically this clone can give us that resolution that we are looking for in this panel. As you can see in this example, when we gate it on CD4 or in CD8, CCR is in the in this axis, and you can see how we can maintain a good resolution between positive and negative. So for that reason, this will be our option for CCR7. Now we have to be careful on how we assign the Pacific blue. Pacific blue has to be in an opposite cell type. And since Pacific blue is a dim dye, we want to assign a very bright or a very abundant molecule, as it is CD20, that is expressed on B cells. That way, we won't do a gating between CD20 versus CCR7, and we are gonna minimize the spreading. And moving forward, I'm gonna show on this table all the markers that we have been assigned. So far we have CCR7 and CD20 plus our zombie NIR for viability. Now, P is another very bright dye, and this dye, again, from internal experience, we know that it works well for TCR gamma delta, as can give us a good resolution or a good identification for this population. And that means that we are gonna take care on how we assign the spark yellow-green 581. Since TCR gamma delta is for T cells, we want to assign the spark yellow-green in a non-T cell type. And here, IgD that is highly expressed on B cells will be a good option. That way, we won't look at TCR gamma delta versus IgD. And even if you do it, you are going to observe this negative spreading error that is common to observe in a spectral cytometry with two dyes that are very similar. However, you still have a good resolution for the positive populations here. And even better, if you do an appropriate gating strategy, you are going to see that IgD is very well resolved when it's conjugated with the spark yellow-green 581. And our last combination for the red laser is APC, Alexa Fluor 647, and spark NIR 685. So in this panel, we want to identify Tregs using CD127. And to identify that population, we need to have a good distinction between the highly expressed and dim expression of CD127. And in order to have that distinction, we need to assign this molecule to a very bright dye. And that's the rationale that we follow to assign this marker to APC, as APC is a very bright dye, as you know. Then we have to be careful on how we assign Alexa Fluor 647. And that means that it has to be in a non-T cell marker. And in this case, we are going to assign CD11C that is expressed primarily in dendritic cells. And finally, we have to consider also how we assign the Spark NIR 685. This is a relatively bright dye, and since we have already used T cells and dendritic cells, here a marker for B cells would be a good option. And we have the option of CD19. I know that CD19 has a high expression, and here we are assigning a bright dye. So we are breaking that rule that I told you before, but we are considering other aspects as the gating strategy and what is the reagent availability that we have for this panel. And if you look into the gating, if you gate against each other, you are going to see again the negative spreading here when you gate them. But there is still the good distinction in the positive for all of them. So that means that so far, this is how our panel is looking. I'm including here in red the markers that we have been assigned in addition of the table. So, and now I'm going to move relatively quickly to show you how we assign other markers, I'll think is relatively self-explanatory. And for example, for CD25, that is low expression, we are going to assign a bright dye as it is P-Fire 700. For CD14, Spark Blue 550. For CD8, PerCP Psi 5.5. For CD3, the Brilliant Violet 570. For CD4, the Spark Blue 574. And for IgM, the Brilliant Violet 510. So far, our panel is looking like this. And let's continue assigning markers. Now we are going to work with two markers that are co-expressed in dendritic cells. And since they are co-expressed in the same cell, that means that we are going to gate them against each other. And we have to be very careful on how we assign the dyes here. They are lowly expressed, so that means that they need a bright dye, but two bright dyes that are different enough to maintain the resolution of both populations. For that reason, we are going to assign CD11C to P size 7 and CD141 to the P Dazzle 594. Now, from extensive internal experience working with the P Fire 810, we know that this dye is a good combination for HLIDR, so we are going to assign that marker to that one. And CD27 in our panel is a particular interest for both B cells and T cells. So that means that CD27 has to be, again, with a fluorophore that is different from other fluorophores that we have already assigned for B and T cells. And following that rationale, APC Fire 810 is a good option for this marker. Now, PD1 in this panel that the interest is to do general phenotyping is going to be assigned to a relatively bright marker that is Brilliant Violet 785. Now, CD56 is going to help us to identify NK cells. But when you analyze the CD56 population, you are going to notice that these markers show up as a trimodal pattern. And in order to maintain that resolution between dim and highly expressed expression of CD56, we have to assign a medium bright marker that will be Brilliant Violet 750 in this case. And when we are going to the end of the markers, the criteria that we are going to follow is the same, assigning highly expressed markers with dimmer molecules and keeping in mind what will be your gating strategy to avoid the spreading. So CD38 in this case was assigned to Brilliant Violet 711. CD45 RA was assigned to the Alexa Fluor 488. CD28 to the Brilliant Violet 650. CD123 to the Alexa Fluor 700. CD16 with our Brilliant Violet 605. And the CD45 to the APC Fire 750. So at the end, this leaves us with this panel. I have included all the markers that we selected today. And this gives us a very well-balanced panel that has distributed the markers based on the similarity index, the gating strategy, and also to minimize the spreading between them. This is the bundle of all the antibodies, and you can find it in our website. And this also includes some other reagents that you are going to need for an optimal performance of these panels, as it is our staining buffers, FC blocks, compensation beads, and etc. And this panel, and together with others in our website, is coming soon as a product catalog for a more convenient ordering. All our optimized panels, they come with an optimized protocols that includes the staining guidance and the suggested gating strategies. In this particular panel, we use 1 million of fresh PBMCs, and then we do the staining, and we do the acquisition in the Cytec Aurora with 5 lasers, and we further analyze the data. And in the following slides, I'm going to show you the type of data that you can get if you use this optimized panel. First, let's start with the myeloid compartment. All our gating strategy follow the same intro, where we are going to identify first the singlets, then the alive cells, and then the CD45 positive cells. From this population, we further identify the CD45 intermediate and CD123 positive cells, and then we look for the expression of HLA-DR and CD11C. We are going to identify here the CD123 positive basophils. Then jumping a little bit back to the CD45 population, now we can do the classical gating for the forward scatter versus side scatter to identify the monocyte population and this lymphocyte, NK, and dendritic cell population. From the monocyte, you can identify classical, intermediate, and non-classical monocytes when you look for the expression of CD14 versus CD16. Now let's analyze the dendritic cells. For the dendritic cells, we are going to start here in the lymphoid, NK, and dendritic cells gating, and we are going to exclude T cells gating on the double positive population for CD3 and TCR gamma delta. Then we are going to exclude also V cells and NK cells gating in the double negative population for CD19 and CD56. And from that lineage negative, if we gate here in the CD14 negative and HLA-DR positive, we are going to identify the CD11C dendritic cells and the CD123 plasmacytoid dendritic cells. And we can do a deeper analysis getting in the CD16 negative dendritic cells and further identify the CD11C positive dendritic cells and the CD141 dendritic cells. Now from the lymphoid compartment, let's start analyzing the NK cells. From the NK cells, we are going to follow a similar gating. We are going to exclude the T cells in the CD3 negative, TCR gamma delta negative. And we are going to select here the CD56 positive, HLA-DR negative NK cells. And here we are going to identify that trimodal population that I mentioned before when we were assigning the marker for CD56. We have the three population or subpopulation of NKs, and we can do a deeper analysis on those NKs to check the expression of CD27 or CD38. Now for the V cells, here we are going to start similarly excluding the T cells, and we are going to identify the V cells gating on the CD19 and CD20 double positive cells. And then we can further identify the memory B cells, the marginal zone-like, and the naive B cells if we gate in CD27 versus IgD. And from the memory B cells, we can go and identify the IgD negative memory B cells or the plasmablast if we gate on CD20 versus CD27. And we can go even deeper and check the expression of IgM and CD38 in this population of B cells. And finally, let's analyze the T cells. For the T cells, we can identify the CD3 positive gamma delta T cells, and we can look for the expression of CCR7 and CD45 array for these TCR gamma delta cells. Or we can do the analysis in the most abundant CD3 positive TCR gamma delta negative, where we can exclude NK T cells here, making or doing the gating on the CD3 positive, CD56 negative, and to further identify the CD4 and CD8 T cells. And from the CD4, we can later do the classical gating for CD127 and CD25 to identify the Tregs. And again, this is one of the markers that we carefully assign CD127 to have a marker that is bright enough to allow us to identify the Tregs here. And again, from the Tregs, we can analyze the expression of CCR7 and CD45 array. Similarly, for the CD4, we can do the same gating to identify the effector and the naive cells and naive, effector, and central memory. And from the effector, if we do the analysis of CD27 and CD28, we are going to identify the terminal effector, the early-like effector, and the early-like effector CD4 cells. And of course, this is just an example of the gating strategy, and you can put your unique spin and expand it as it is best for your research. And again, I would like to invite you to visit our website, where you are going to find 3 more panels that includes the human T cell differentiation and exhaustion, or the human T cell differentiation and CCR. Both are the 27 colors panels. We have the human general phenotyping panel that we just built together today. And we have 3 more panels that are coming soon. One is the human myeloid panel, 27 colors, the human Tregs, and the expandable panel. That maybe this expandable panel will be useful for your research also, as leaves ties open for an easy expansion. This panel comes with some basic markers to identify T cells, B cells, myeloid cells, but leaves many fluorophores with high reagent availability. That way you can easily expand it and put the markers that are more relevant for your research. And with that slide, I would like to conclude that BioLegend customers benefit from the experience and expertise of BioLegend scientists, as you can save time, energy, and money on optimizing your panels if you leave that part to us. And also, you can have insider insight on the most optimal panels, markers, clones, and conjugate selections. You are going to receive detailed protocols that include the best buffer usage, antibody dilution, and ideal staining conditions. And you can also receive gating strategies for ideal population visualization. That way, you can spend more time focusing on driving your research forward to legendary discoveries. And finally, I would like to thank especially to Rebecca Nicol, as she was working really hard on optimizing these panels. And I also want to thank Eduardo and Lisa. They are our research associate that have been helping us doing the experiments and doing the panel optimization. I also want to thank the PD team that includes also our Fluorophore manager for their support in the optimization, and Miguel, that is our manager for the marketing, and Carsten, our vice president of marketing, that they've been also very useful, guiding us and giving us feedback during the panel optimization, and in general to the marketing team, especially the project managers for flow cytometry, as they have give us a good feedback for the optimization, but also for the rest of the marketing team for organizing this workshop and for organizing other activities that we have prepared for AEI. So thank you, and be on the lookout for more panels to come. Okay, now I'll be happy to answer any questions if you have.
So based on the literature, we think some markers are negative for some specific cell types, but in fact, sometimes we find the molecule is really expressing. For instance, you said CCR7 and B cell marker CD20 in the BB421 and the Pacific Blue. And B cells are relatively lower than T cells for CCL7, but B cells are actually positive for CCL7. So in that case, I'm wondering if those two markers conflict and we have some wrong interpretation. Is that happen, or we can completely distinguish those two signals?
Yeah, I think for our human general phenotyping panel, you can distinguish them very well. And also your gating strategy is going to help you to distinguish what signal is coming from the B cells versus the T cells. But when you do the unmixing, we can observe a very good resolution for both if you gated them against each other. So you are going to observe that spreading error in the negative but the positive populations are well distinguished. Again, sometimes it's going to depend of the cell type or the sample that you are analyzing, how abundant are those molecules in your sample. But at least for the human general phenotyping panel, they have a good resolution.
Hi. I think the panel design you described is based on the experimental experience, right? Human experimental experience. What do you think about the panel design through machine learning in the future, maybe?
You mean using AI? I'm not sure if we are already ready for that part. I think there's been some people trying to use AI to come out with the best combination of fluorophores and dyes, and it's not always working as it is, in theory, in paper, in reality. So I think at least at this point, we are a little bit not ready or far from that option. That is not exactly, you cannot translate what AI is saying to the actual experiment, at least at this moment. Maybe in the future, we are going to have a better technology that allows to give us the best combination among all of them, but not at this point, I believe so. Any other question? Okay, thank you so much for attending the workshop.